We hear the term neural network all the time. It powers the apps on your phone. It writes poems, drives cars, even paints portraits. But stop for a second. What actually is a neural network? Is it a brain in a box? A machine that thinks? Or just another fancy name in the world of buzzword tech? The truth is, neural networks are behind some of the most advanced artificial intelligence systems today. But most people have no idea how they really work. They're not magic, they're not alive, but they're designed to mimic something that is the human brain. In this deep dive, we're going to pull back the curtain. We'll break down what neural networks are, how they're built, how they learn, and what they can and can't do. Ready to crack open the mind of the machine? Let's begin. To understand where neural networks come from, we need to go back to the original network, your brain. Inside your head are around 86 billion neurons, tiny cells, constantly firing electrical signals to one another. Each neuron connects to thousands of others through little junctions called synapses. It's this web, this biological network, that makes thought, memory, and learning possible. In the 1940s, scientists asked a bold question. Could we build something like that? A network made of math instead of biology. By the 1950s, early computer scientists created simple models that mimicked how neurons respond to input, firing only when certain thresholds were reached. The idea evolved. In the 1980s, we got backpropagation, an algorithm that lets neural networks learn from their mistakes. And with faster computers, more data, and better math, neural networks exploded in capability. From simple pattern recognition to beating world champions at complex games, these digital brains started to rival our own in surprising ways. But while they're inspired by biology, they're not brains. There's something entirely new. And next, we'll look at how they're actually built. Now that we've seen where the idea comes from, let's look under the hood. What is a neural network made of? And how does it actually work? At its core, a neural network is a chain of layers, each one filled with digital neurons or nodes. It starts with the input layer, where raw data, like images, sounds, or numbers, enters the system. Each input connects to a web of hidden layers, the real brain of the operation. These hidden layers process the data using a system of weights, which determine how important each connection is. Think of weights like volume knobs, adjusting how much each input matters. Then comes the activation function, a mathematical decision-making. It decides whether a node should fire or not, based on what it receives. It's like a switch saying, yes, pass this forward, or no, stop. The signal moves through layer after layer, getting transformed and refined at each step, until it finally reaches the output layer. Here, the network delivers its best guess. That's a cat. This email is spam. Or turn left at the next intersection. All of this happens in milliseconds. And while it looks like magic, it's just math flowing through a beautifully designed web of connections. Simple pieces stacked together, creating something surprisingly intelligent. So we built our neural network. Now comes the hard part, training it to think. But how do you teach a machine? It starts with forward propagation. You feed in data, say images of cats and dogs. The inputs move through the layers, triggering nodes, getting transformed at each step until the network makes a prediction. Maybe it says 80% dog, 20% cat. But if the actual answer was cat, that's a mistake. So now the network calculates loss, a number that tells it how wrong it is. Think of it as the machine's version of oops. Then comes backpropagation. The network works backward from the mistake, adjusting its internal settings, those weights and biases little by little. The goal? Reduce the loss. This process repeats thousands, sometimes millions of times. Each time, the network gets a bit better. Bit by bit, mistake by mistake, it learns. The tool that helps fine-tune these changes is called an optimizer. It's like a coach, guiding the network toward better predictions with each training cycle. The result? After enough iterations, the neural net can recognize patterns with astonishing accuracy, even in things it's never seen before. Not magic, not intuition, just math, repetition, and a lot of data. So far, we've been talking about neural networks in general. But here's the twist. Not all neural networks are created equal. Just like there are different tools for different jobs, there are different types of neural networks, each specialized for a certain kind of task. Let's start with convolutional neural networks, or CNNs. These are the visionaries of the AI world. Literally, they're designed to recognize patterns in visual data. Whether it's faces, handwritten digits, or street signs, CNNs are great at analyzing images by scanning them in chunks, layer by layer, like looking through a microscope that sharpens the details as it zooms in. Next up, recurrent neural networks, or RNNs. These are the time travelers. They're built to handle sequential data, like speech, music, or text. They remember what came before and use that memory to make better predictions, making them perfect for tasks like language translation or voice recognition. And finally, we have the rising star, transformers. These networks are revolutionizing how machines understand language. Unlike RNNs, transformers can look at an entire sentence all at once, capturing context, tone, and relationships between words with incredible accuracy. They power large language models, chatbots, and AI that can even write stories. Each of these networks has its own strengths, its own niche, and together, they're building the foundation of today's AI revolution. Neural networks aren't just clever theories or lab experiments. They're already everywhere, working behind the scenes in ways most of us don't even notice. Ask your phone a question, and a voice assistant, like Siri or Alexa, converts your speech into text, understand what you meant, and responds in seconds. That's a neural network trained on language and sound. Ever wonder how your bank flags suspicious transactions before you even notice? That's fraud detection powered by neural nets, spotting patterns in data that human eyes might miss. Browse Netflix? The recommendations you get aren't random. They're chosen by algorithms trained on your viewing habits, using neural networks to predict what you'll love next. In healthcare, neural networks help doctors detect early signs of disease, analyzing medical scans faster and more accurately than ever before. And in the world of art, AI now creates paintings, music, even full-blown movie trailers. Tools like DALL-E and Midjourney turn words into visuals, imagination into output. From finance to medicine to creativity, neural networks are already shaping how we live, work, and express ourselves. And we're just scratching the surface. For all their power, neural networks aren't perfect. In fact, some of their biggest challenges are the ones we don't always see. First, there's overfitting. This happens when a network memorizes its training data too well and struggles with anything new. It's like studying only past exam answers and failing the real test because the questions changed. Then there's bias. Neural networks learn from data. And if that data is biased, so is the output. From facial recognition errors to unfair hiring algorithms, the consequences can be serious. Another issue? The black box problem. Even the people who build these networks don't always know why they make certain decisions. You feed in data, it gives you an answer, but how it got there, that's often a mystery. And finally, energy. Training large models takes enormous computing power. We're talking about massive GPU farms using as much energy as entire towns. It's fast, but it's not free. So yes, neural networks are powerful, but like any tool, they have limits. And as we race ahead, it's just as important to ask, should we use them for everything? And how do we make them better? So what's next for neural networks? The future is about learning that never stops. Imagine machines that don't need retraining from scratch, but learn continuously like humans do. It's called continual learning, and it's one of the big frontiers ahead. Then there's explainability, giving AI the ability to not just make decisions, but explain why it made them. No more black boxes, just clear, understandable logic behind the output. And maybe the most exciting? Quantum neural networks. What happens when we combine the raw power of quantum computing with the structure of neural nets? We're not sure yet, but it could lead to breakthroughs we can't even imagine. One thing's certain, neural networks are evolving fast. And if the past decade was impressive, the next one might just be revolutionary. So stay curious, stay informed, because this is just the beginning.